Okay, here in part two, I got a little long-winded in part one there. Here in part two, we're going to talk about string instruments and frets. And so, instruments, you've got the length of the string. That doesn't change. You've got a fret position, you've got the wavelength you're after, you've got the frequency you're after, you've got the speed of sound, all of those things. So let's think about the different types of string instruments. Pianos, harps, harpsichords, lyres. Those are simple because you're not changing the length of the string. You've got one string per note, and so you design each string and tune each string to the note you're after. But then you've got guitars, mandolins, violins, lutes, and instruments like that. You're going to tune the strings while playing by effectively changing their length. And so you're going to either you can be fretless or you can have a fret, but you're going to put your finger onto the string and basically pin one end down in a different place. So if you think of this as our string we're talking about, and this is from bridge to fret, and this is our nominal length of the string, so you've not done anything with it at all, it's got some length L. And this is going to be our fundamental frequency for this string, F1. It's the wave velocity over lambda 1. We know for a string, your wavelength is twice your length, so wave velocity frequency is just wave velocity over twice the length. Okay, that's fine. Um, so we know what frequency we have. We tune to a particular frequency, but then we want some other frequency in here. Now, Fn has to be greater than F1, right? It can't be lower than F1. You can only go up because you're shortening the length. Because you make lambda shorter, F has to be higher, all right? And so you want to figure out, okay, I've got I don't know, I've got a G here and I want this to be an A. How do I, and you go back to your chart on frequencies and you figure out what frequency you're after and you're hearing like, okay, what length do I need for this to be down here? And so let's take a look at that. So first, the wave velocity is lambda 1 F1 is 2L F1, right? And so we can write right here, we can write Fn as F1 times L over Ln. Well, you know what frequency you're after. That's not a mystery, I hope. I hope you're not picking lengths and then going, well, whatever frequency I get out of that, that's what I get. Um, I, I guess you could do that if you're playing jazz. Um, so here you are, and you've got your frequency, your fundamental frequency, you've got your frequency you're after. And when you solve for where do I need to put the fret, this Ln. Ln is your fundamental length times the ratio of your frequencies, F1 to your higher frequency, right? And you can see Fn, as I said earlier, is going to be greater than F1. So Ln is always less than L, right? If you want to make Fn um, lower than F1, then you end up with having to lengthen the string. Really hard to do while you're playing, right? Lengthening the string. Um, let me just grab a longer guitar real quick. It's about all you could do. So this is how this is how you go through and um, you figure out the lengths that you need your fret at, or the positions you need your fret at. And this is distance from bridge to fret. Last thing we're going to talk about are beat frequencies. So you've got two sources of frequencies, two source frequencies, F1 and F2. We're going to define their average. We're going to define the beat frequency. And so let's take a look at what that means. All of you have experienced this in band or some point where somebody plays the wrong note and it makes this awful beat sound. Well, let's look at the math for a second. All right. The math is if I take two sine waves and I simply add them together, I can use some trig identities, and what I end up with is this sine wave multiplied by that sine wave. Oh, let me rewrite this real quick. And so what's that going to give me? That's going to give me a sine wave that looks like this. All right, it's going to give me a sine wave that is at the average frequency times a cosine wave that's at the beat frequency. All right. Again, I've got my average frequency, which is just the average of the two frequencies. I've got my beat frequency, which is half their difference, and you'll see there's a magnitude here. There's not a magnitude here, but since the cosine is symmetric around f1 minus f2 and f2 minus f1, we're going to define the beat frequency as the positive difference. And so I take the magnitude here. And so you end up with this 2 sine of 2 pi f a times t times cosine of 2 pi f beat times t. So these are multiplied together, right? And what does that look like? Well, here I've got a 100 hertz wave I've graphed, and I've got a 105 hertz wave graphed. So there's a beat frequency here that's 2.5 hertz, right? 2.5 hertz. What is 2.5 hertz in terms of seconds? 1 over 2.5. So, that's going to give us a beat frequency. Let me calculate that real quick. Of 0.4 hertz. So let's go back to our slide deck. All right. All right. So beat frequency is 0.4 hertz, and you can see here, all right, I've added all this graph is these two added together, and you can see I've got now right here, it takes 2 to see the beat frequency. Right here, as predicted at 0.4 hertz, we've made a full cycle. You're going like, that looks like 2 full cycles. Well, actually, it's this, 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 and that is the positive, and there's a switch over here where you get negatives and then switch back to positives. So at 0.4, you get 1 full beat cycle. And this is actually very important when you play tune a piano. If you look at a high-end piano, there will be 2 strings next to each other, and the 2 strings are tuned slightly differently. And they're tuned slightly differently because you get the average frequency, which is what you hear as the note, but then you get this sound that evolves over time, and it gives us a richer experience of the note than all of you have played monotones on your phones at this point, and they're extremely boring, right? And so by doing this, we make the piano sound much less boring with this evolving note over time. All right, that's it for this overview of these slides. And I'll have everything else posted shortly. Have a great day.